So this is the last topic of the course, which is on Markov chains. So this is covered in the last chapter of the handbook, which is on bright space. And it's not in the textbook, so and so therefore, unfortunately for this one, there's no whatever study guide, right? On MyLab Math. But there are some practice questions in the actual, like right in the handbook. So, and they have answers. I think you should find them helpful for this. So yeah, if you're looking for this in the textbook, you're not going to find it. Actually, if you look for this in the textbook, you're going to find the wrong thing, because there is a chapter about Markov chains in the textbook. It covers the wrong content. So don't use the textbook for this. Any questions about this? Yeah, there were some questions about the test. Maybe I'll just address those quickly. So test 3 is during the exam period. Okay, and then it's going to cover everything that wasn't covered on the last 2 tests. So everything in the course that wasn't on the last 2 tests, all the way up to what we'll do on the last day of classes. I think that starts with like maybe matrix arithmetic with matrices or something, like adding and multiplying matrices. Goes through like, I think, inverses and all this stuff on Markov, all the linear programming stuff on Markov chains that we're going to do now, and stuff like that. And it's, by the way, it's not like a 3-hour exam. It's the same as all the other exams, or all the other tests. So just 15 minutes. Any questions about anything at the moment? Yeah?
Is it here or is it?
It's in the gym. Yeah. Yeah, so if you look at you have an exam schedule or whatever on, if you Google UVic exam schedule, it's at the location that it says on the exam schedule. So it's not in this room. There's 3 sections in this course. You'll all be in the gym at the same time and writing at the same time. I think it's like 7 p.m. on December 12th, yeah. But yeah, check the exam schedule. Okay, so here's so we kind of talked a little bit about Markov chains at the end of last class, but that was a long time ago now. So here's the kind of setup. So imagine a system. It's not really. This is going to be a little bit imprecise language. I'll just say, but hopefully it'll become clear what I mean as we go through some examples. But imagine you have some kind of system that can have, k different states, where k is just a number, it's an integer. So your states could be like, I don't know, on or off or something. Your states could be sunny, like it could be, you could be kind of modeling the weather. It could be sunny, rainy, snowy or something. Could be, you know, a person could be awake or asleep, you know, anything that basically you could describe it, you know, there could be different states and you want to kind of analyze this process where the system moves between different states. So in each step, the system will transition from one state to another. Okay. So you can think of it like if you think of this weather example, each day, like one day we'll have some kind of weather, and then the next day it'll transition to maybe some other type of weather. Or maybe you could even think minute by minute, the weather might change. Okay? And the way we kind of model this is we think of, you know, whatever state you're in, there'll be a certain probability of changing to any other possible state. So the probability so kind of a key assumption in a Markov chain is the probability of moving from one state, from state, let's say state I, where I is just a number, to state J, is a fixed number that doesn't depend, that only depends on I and J. So basically what I'm describing here is a k-state Markov chain. So basically the concept here is like, basically like, if we're doing this thing about weather, the probability, if it's sunny today, the probability that tomorrow is rainy, we kind of think of that as not depending on the previous history of the weather. So basically, like maybe, you know, on every sunny day, the next day is rainy with probability 40% or something, or 20% or something. So the thing is, so Markov chains basically are used to model a lot of different things. For example, you know, things involving you know, economics and things like that. But yeah, let me give you an example, and then it might become a bit clearer. So let's say that Jill goes to the casino with $2. Okay, that's not a lot of money to go to the casino with. And she plays a slot machine And this is like the simplest slot machine in the world, okay? It costs $1 to play. So each costs $1. Okay, so there's no other options. You just put $1 in the machine, and 45% of the time, it gives you $2 back. So with probability 0.45, it returns $2. And with probability 0.55, it gives you nothing. Right, just your dollar goes in and nothing comes out. So she will give up. She gives up if, like, she's going to play for a certain amount of time, put in $1, put in $1, and she's going to give up. Obviously, if she has no money, she has to give up. And then the other condition is if she doubles her money, so if she ends up with $4, she's going to say that's good enough, and she'll give up. So if she has $0 or $4 in total. So otherwise she's just going to keep playing. Okay, so I want to kind of think of this as a Markov chain. So we have a certain number of states. When she starts the game, the state of the system is that she has $2. Once she plays the game, she's going to put in $1. Either she's going to end up with a total of $3, right? Because it'll give her back 2, or she'll end up with a total of $1, right? So it turns out this is a 5-state Markov chain, where our states are that she could have, $0, $1, $2, $3, or $4. She can't go higher than $4 though, because if she gets to $4, she quits, right? So these are our 5 states. And then if you think about it, from any given state to any other state, there's a fixed probability of moving from that state to the other one. Like the probability of going from $2 to $3 in a given step is 0.45, right? So basically, for these two states, the probability of going from this state to that state, it doesn't depend on the previous history, right? She may have played 100 times up to this point, and now this is the 101st time. The probability is going to be 0.45, or at the very beginning, the first time she plays, it's still 0.45. It doesn't depend on the history of the game. So that's like the key feature of a Markov chain, that the only thing that matters is where you are now, what state you're in now, and what one you're going to. That's the only thing that determines the probability. So for example, going from, similarly going from $3 to $4, also has probability 0.45, going from 3 to 2 has probability 0.55. And then there's a bunch of other events that also have probabilities, because, like, for example, going from $1 to $4, that can't happen, right? So like $1 to $4 has probability 0. Because you're only going to go up or down by $1 every time. Any questions about this so far? Okay, so basically what we want to do is so when you have a Markov chain, you can represent it with two matrices. So Markov chain can be represented by an initial state matrix and a transition matrix. Okay. This initial state matrix tells you where did you start the process. So in this case, the initial state, like where we started was with $2, right? So that tells us the initial state of the process. And the transition matrix tells you the probability of moving from one state to another. So this is, this indicates where the process started. And this indicates transition probabilities. Okay, so in this case, our initial state matrix would look like this. So the kind of typical notation for the initial state matrix is you write S with a subscript 0. Okay. One thing about Markov chains is you have to come up with a simple way of kind of, like the matrices depend on how you decided to order your states. Here I think it's kind of obvious, we should just order them like the first state is $0, then $1, then $2, then $3, then $4. So you don't always necessarily have to label your columns like this, but basically I want to say that this is what each state, each column represents a state. And where the process started is, so with 100% probability, so with probability of 1, the process starts with $2 as the state. So this means with probability 1, she starts with $2. If you have a slightly different game where at the beginning of or a slightly different scenario where at the start she flips a coin, and if it's heads, she brings $2 to the casino. If it's tails, she brings $1. Then you have like a 0.5 here and a 0.5 here to represent those probabilities. Okay, and then my transition matrix. So this is the initial state matrix. So the transition matrix we usually call P. The P kind of stands for probabilities because it's a matrix of probabilities. So this matrix, again, it's going to have a column for every possible state, and it's also going to have a row for every possible state. And then in each row, what you're going to do is you're going to write the probability of, so in each entry, we write the probability of going from the state on that row to the state on that given column. So let's look at this row first. So from $2, there's no way to go to $0. So I'm going to put a 0 here. Right? The probability of going from $2 to $0 is 0. The probability of going from $2 to $1 is 0.55. If you play the game, the probability of going from $2 to $2 is actually 0, right? You can't stay the same. You either go up by $1 or down by $1. So that's 0. Here's 0.45 and 0. And then, yeah, you've got similar things for the other rows. So on the row for $3, right, the entry corresponding to $2, the column of $2 is like the probability of going from $3 to $2. Okay. There's something a bit weird about $0 though, right? Because if at any point she ends up with $0, she doesn't play anymore. So in some sense, the transition probabilities in that case, like basically if she has $0, then she's going to stay with $0 forever. So what I want to do here is say the probability of going from 0 to 0 is 1, because once she has 0, she only transitions back to 0 forever. She doesn't, nothing else happens. Then similarly for $4, she'll have $4 forever. Right? Okay, so generally speaking, the initial state matrix is like some matrix S0, which is like, so capital S0, I'll write this as little S01, S02, dot, dot, dot up to S0K, where for any index I, S0I is the probability of starting in state I, or starting in the I state. Oh, by the way, this P is your transition matrix. So P is going to be like P11, so it's a K by K matrix. You have K states. P12 to P1K, P21 down to PK1. So in these subscripts, the first one's always the row, and the second one is the column. So this is like row 2, column 1. So where Pij is the probability of going from the I state to the J state. But yeah, I mean, really, just think of this example. You know, when you're at $2, the probability of getting $1 is 55%. That goes in this column. The probability of getting $3, 45%, that goes in this column. Any questions about this? Okay, here's a, I don't know, a little kind of theoretical question. Like what happens if you add up the entries of S0, what do you get? So I don't mean just in this example, but like in total, in general. So the ith entry should be the probability of starting in state I. And yeah, what would you get if you add up all the entries? Does it depend on the Markov chain? Yeah. Oh, yeah. So I didn't know if you were raising your hand or not, but I assume that's your answer. Yeah. So you get 1, right? Okay. So if you're setting up a Markov chain and you look at your initial state matrix and it doesn't add up to 1, you've got a bit of a problem because probabilities, if you add up all the probabilities, they should add up to 1, right? Because there's k different states, each of them should have some probability, and yeah, they should add up to 1. And the same thing is true, so the sum, so if I take any row of this matrix, so the sum of any row of the transition matrix P should also be 1 as well. But it's not true for columns. Right, because you can see here, this column adds up to 1.55. You know, this column adds up to 0.55. This one actually does add up to 1, but that's just a coincidence. Generally speaking, the columns don't add up to 1, right? Any questions about any of this so far? Okay, so here's the nice thing. We can take these matrices and we can use them to figure out, using matrix multiplication, we can determine the probability of being in any given state after any number of steps. So given S0 and P, we can compute S1, which is going to be S0 times P, where here we're doing matrix multiplication. Okay? And this is going to tell us, so, well, actually, let's just do it in this specific example. So our matrix is like, so I'm just writing out the matrix again. Well, the two matrices. A little bit. 0 point. Okay, this is a little bit hard to see. But I'm just writing out the same matrix again. I recommend doing it a little bit less messy than I do. But if we apply this matrix multiplication, remember how that works. We take this row, and we multiply it down this column. And that should give us the entry in the first row and first column of this matrix. So I get 0 times 1, 0 times 0.55, 0 times 1, or sorry, 1 times 0. So everything is 0 when I multiply here. I then get, right, 0, 0, but then this is 0.55 times 1, which is 0.55. And then everything else is 0. So I'm just applying the rules of matrix multiplication. 0 times 0, 0 times 0.45, 1 times 0, 0 times, so it's going to be 0. Then you'll see that this one's 0.45, and the last entry is 0. Yeah, it's so hard to see, but yeah. These are the columns here. Yeah, okay. Sorry, I kind of wrote that kind of messy. But basically what I want you to see here is that what this matrix does, what this operation does, we started with the initial state, which was $2, and when we multiply by the matrix, it gives us the number here, which is 0.55 on $1 and 0.45 on $3, which is actually the same as the probability of getting $1 or $3 after one step of the process. Okay, and that's generally how this works. Multiplying by the matrix, the transition matrix, kind of moves you forward one step in the process. So if S1, so S1 is this, right? If I write its entries as S1, S12, up to S1K, if I take any S1I, that's the probability of being in state I, or the ith state, after one step. Okay. More generally, if I keep doing this process, if I take Sn, if I start with my initial state, S0, and then I do n transitions, which is like multiplying by p n times, which we can write as S0 times p to the power n. So p to the power n just means multiply p by itself n times. So this matrix will tell you the probability of being in any given state after n steps. So to tell us the probabilities of all states after n steps. Here's a question. What happens if I take Sn and I add up all its entries? It's kind of the same trick, I mean not a trick question, but same question as before basically, right? It should be 1, because if I take 100 steps and I look at all the different states and I say, what are the probabilities of being in all the different states? And I add them up, it should add up to 1, right? Because you have to be in some state. Okay. So if we apply this in this specific case, so yeah, S1 was just this matrix, this row matrix. If you apply it again, you'll see that like so I'm not gonna do the calculation, but well, so I've written this Sn as S0 times like p to the n. You can also say this is the same as taking S1 times p on the correct side, right? Because it's the same as, because it's, for S1 I had to already multiply by p once, so this is multiplying by p again. And if you do the calculation, you'll see that this is 0.3025, 0.495, 0, and then 0.2025. So from this information, if I ask, like, what is the probability that Jill has $2 after after playing twice, then what would you say? Yeah. Yeah, right? Because it's just this number, right? Because remember, this represents $0, $1, $2, $3, $4. So this is the probability of having $2. Right? You can also say, what's the probability of that she goes home after that she quits? So quitting after 2 plays, right? In that case, you'd have to, oh yeah, go ahead. Yeah. Probably something like that. It's whatever you get by adding up that and that, right? Is that where you're, yeah. Right, so then we take 0.3025, which is the probability of having $0. But she also quits if she has $4, so 0.2025, which is 0.2025. 5, 0, 5. Is that right? Okay. So basically, if you want to take n steps of the process, you want to multiply by p n times. Note that it's important that I'm multiplying on the right side, okay? Because remember, matrix multiplication, you can't just do it both ways. So multiplying on the left side, in fact, in this case, it wouldn't even make any sense. So you always want to take your initial state or your current state and then multiply by p on the right side. Any questions about this? Okay. A lot of this stuff that we're doing here, by the way, we kind of already had tools for this. Because we already knew how to draw tree diagrams. Like all of this stuff I'm talking about here, you could have done the tree diagram, right? Because you could say, she starts with $2. She goes to $3 with probably 0.45. Right? This is totally stuff we could already do. Right, if we wanted to understand what happens after 2 steps, 2 plays, this tells you everything, right? Because you could say, what's the probability of having $4? You take this number times this number, because that's the only way to get $4. You'd say, okay, what about $0? You take this number times this number. You should get the same thing as over there. If you say $2, you have to go, $2 would say this path plus this path. So you'd multiply those and add it to the sum to multiplying those, right? So in some sense, so far there's nothing new, okay? But where the new stuff comes in is when we start to ask different questions, which are kind of, would be really hard to answer with a tree diagram. So, for example, we could ask, so here's a question that's hard to do with a tree diagram. For example, what is the probability that she has $4 when she quits? So the reason this is hard to do with a tree diagram is because the tree diagram would have to be huge, right? Because, okay, we can compute this probability easily. The probability she gets $4 in 2 steps. But she might get $4 after 100 steps, right? Because she might go, $2 down to $1 to $2, $1, $2, back and forth up to $3. Like she might just do this for a really long time and then eventually get to $4 and then quit, right? And that can happen for any number of steps. So in some sense, to answer this with a tree diagram, you kind of need like an infinitely large tree diagram to cover all the possible cases. And obviously that's not feasible. So basically we're going to be able to answer questions about these kinds of things without using a tree diagram and just by analyzing the matrices. So before we wrap up, let me just give you a few quick little questions to test. Kind of understanding of these transition matrices and stuff. So here's a question. So can this matrix be a transition matrix of a Markov chain? So what if I do 0.3? So let's think about that, and then when you know the answer, maybe give me a thumbs up or a thumbs down. Could that be the transition matrix? Okay, it looks like most people are saying no. Can anyone tell me why? Yep. Yeah, it's kind of trying to trick you, right? Because the columns add up to 1, but the rows don't. So the answer is no. Rows don't add to 1. But if I kind of switch this around, then this example would be yes, right? Okay. So yeah, we'll continue with more examples like this next time.